Imagine you're flying a multi-million-dollar tactical drone, right? You're over a contested environment. You are looking at your screen, tracking the telemetry, and, everything is green.
Sounds like a good day so far.
Right. But suddenly, an enemy truck parked on a hill 3 miles away powers up this massive truck-mounted generator and just blasts the entire sky with a wall of electromagnetic noise.
Oh, wow. Yeah, that changes things.
Exactly. Based on basic physics, your drone should go blind. I mean, it should instantly lose connection, lose its GPS, and just fall out of the sky like a brick.
Which is what a lot of people would expect to happen.
But it doesn't. Instead, in the literal blink of an eye, the drone's radio hardware just vanishes from that specific frequency. It begins hopping to entirely different frequencies, 2,000 times every single second.
2,000 times. Yeah, it's staggering.
And simultaneously, an array of antennas on the drone's hull calculates the exact mathematical location of that enemy truck. It creates this digital, highly targeted blind spot aimed precisely at the jammer, effectively deleting the noise from its own reality.
It's incredible.
And it does all of this in 1,000th of a second. And your screen doesn't even flicker.
It is a level of automated resilience that feels almost biological. We're looking at machines that are adapting to hostile environments at speeds that human cognition simply cannot process.
And that is exactly what we are unpacking today on this deep dive. We know you are here because you want to get past the surface level talking points. You want to understand the actual mechanics of the invisible world around us.
Oh, absolutely. The real nuts and bolts.
So today we are taking a massive stack of source material. We've got deep engineering specifications, strategic technical white papers, and these incredibly dense military standards, specifically the STD 461G and H revisions.
Some light reading.
Right. And we are going to decode the hidden nervous system of modern unmanned aerial vehicles. We're mapping out the physical radio waves, the data protocols they speak, and, how they navigate an increasingly crowded sky.
It's a fascinating journey because the evolution of this technology really mirrors our own physical development. I mean, we have to start at the absolute base layer.
Okay, lay it on me.
Well, before a drone can process a complex AI algorithm, before it can digitally identify itself to an air traffic controller, it has to maintain a physical connection to the world. A lot of people assume the wireless technology controlling a high-end drone is basically just, a scaled-up version of the Wi-Fi router sitting in their living room.
Which honestly is a completely understandable assumption. If you look at a consumer drone's spec sheet, you see 2.4 gigahertz or 5.8 gigahertz.
Right.
And you look at your home router, and those are the exact same numbers. So the natural thought is, okay, my drone is basically just a flying laptop.
Yeah, that makes sense on the surface.
But when you dig into these military standards and commercial engineering specs, you realize the spectrum breakdown is vastly more complex. I was reading through the section on the 1.4 gigahertz band, specifically the S-band from 1430 to 1444 megahertz.
The S-band, yes.
The sources describe this as the absolute gold standard, like the dedicated backbone for commercial and civilian drone telemetry. Why is this specific, relatively narrow band so incredibly vital?
It fundamentally comes down to the physics of wave propagation. The electromagnetic spectrum is vast, but radio waves behave very differently depending on their exact wavelength.
Right.
To understand the 1.4 gigahertz band, you really have to look at how it interacts with physical matter. It possesses this incredible capacity for diffraction.
Okay, let's unpack diffraction, because I tend to think of radio waves like a laser beam. Like if I shine a flashlight at a wall, the light just stops. But radio waves don't always do that.
They don't. Think of radio waves more like water ripples in a pond. If you drop a stone in a pond and the ripples hit a large rock jutting out of the water, the waves don't just stop completely.
They kind of wash around it.
Exactly. They wrap around the edges of the rock. They bend. That bending is diffraction. And the 1.4 gigahertz wavelength is positioned right in this physical sweet spot.
Oh, interesting.
Its wavelength is long enough that it can effectively bend around geographical obstacles, things like hills, buildings, dense tree canopies. And it does this without immediately losing all its energy.
So it's sort of hugging the terrain.
In a way, yes. It penetrates foliage incredibly well compared to higher frequencies. The engineering specs we have show that by utilizing this specific S-band, operators can maintain a highly stable line of sight, or LOS, data link for up to 40 kilometers.
40 kilometers? That's massive.
It is. Even if a drone diffs slightly behind a ridge, or if you are flying in an environment with dense physical clutter, that 1.4 gigahertz signal has the physical properties necessary to punch right through and keep the connection alive. It is essentially the deep, steady heartbeat of the drone's control system.
I love that analogy. It's like listening to music from a block away. You can't hear the vocals, you can't hear the intricate guitar solo, but you can feel that deep bass beat thumping right through the concrete walls of your house. It travels forever.
That is an incredibly accurate way to visualize it. The 1.4 gigahertz band is that deep bass. It provides a highly reliable long-range pulse. But just like a bass beat, it doesn't carry a massive amount of intricate detail.
Ah, so there's a trade-off.
Always. It's bandwidth. The actual size of the pipe carrying the data is relatively narrow. You can easily send GPS coordinates, battery status, and simple joystick commands over it. But you cannot send dense data.
Which brings us to the high-pitched whistles of the radio world, the 2.4 and 5.8 gigahertz bands, because I'm looking at the requirements for modern tactical operations and even high-end pipeline inspections.
Right, they need eyes on the target.
Yeah, they aren't just sending numbers back to the pilot. They are streaming live, 1080p, sometimes 4K optical and thermal video in real time. You can't squeeze that high-definition video through the narrow pipe of the 1.4 gigahertz band.
You simply can't. It's a fundamental limitation of physics. The higher you go in frequency, so moving up to 2.4 or 5.8 gigahertz, the shorter the wavelength becomes. And shorter wavelengths allow you to encode vastly more data into the signal per second. You widen the pipe.
But because the wavelength is shorter, it loses that magic diffraction property. It stops bending around the rocks in the pond.
Precisely. It becomes much more directional and, frankly, fragile. A 5.8 gigahertz signal carrying your gorgeous 4K video feed will get completely absorbed or scattered by a dense patch of wet leaves or a concrete wall.
Oh, wow.
Yeah, it requires a much stricter, clearer line of sight. And this physical fragility introduces a massive engineering headache known as multipath fading.
Multipath fading. This is mentioned constantly in the documentation, usually alongside a specific modulation technique called OFDM, orthogonal frequency division multiplexing.
Yes, OFDM is huge here.
The sources present OFDM as the ultimate savior for high-frequency drone communication. But let's break down the problem first. What exactly is multipath fading doing to the drone?
Well, imagine standing in a massive rocky canyon and shouting a long, complex sentence. Your voice travels directly to the person across the canyon, but it also bounces off the left wall, the right wall, and the floor.
Okay, I can picture that.
Those reflected sound waves take a slightly longer path to reach the listener. So by the time your friend hears the end of your sentence, the echoes of the beginning of your sentence are overlapping and crashing into the new words.
It just becomes a garbled wall of noise, like the signal is destroying itself.
Yes, in urban environments, or if you're flying low over water, the drone's high-frequency radio signal bounces off glass buildings, metal structures, and the surface of the water.
Right.
So the receiver on the ground is suddenly bombarded by the primary signal, plus dozens of slightly delayed echoes of the exact same signal. The data stream overlaps, the bits crash into each other, and the video feed completely degrades into static. That is multipath fading.
So how does OFDM, this orthogonal frequency division multiplexing, actually fix the canyon echo? Because the math behind this in the white papers is staggering.
It is brilliant engineering. I mean, instead of shouting one very fast continuous sentence into the canyon, OFDM completely changes the strategy. It takes that massive high-speed stream of 4K video data and digitally chops it up into hundreds, sometimes thousands, of much slower parallel data streams.
Okay, so instead of one person shouting incredibly fast, you have 100 people whispering slowly at the exact same time.
Exactly. It transmits these parallel streams simultaneously on what are called subcarrier frequencies. But here is the critical mathematical magic.
Right.
The word orthogonal.
Right, that's the O in OFDM.
These subcarriers aren't just random frequencies placed near each other. They are mathematically structured to be precisely orthogonal to one another.
Orthogonal meaning they don't intersect, like lines on a graph.
In radio physics, it means the peak of one frequency's wave aligns perfectly with the null or the 0 point of the adjacent frequency's wave. Even though they are packed incredibly tightly together in the spectrum, they do not interfere with each other.
That is wild.
Right. They are mathematically invisible to their immediate neighbors.
I mean, just the processing power to do that on the fly is insane.
And because each individual stream is transmitting data at a much slower rate, even though the combined total is massive, the echoes in our canyon analogy are stretched out.
Oh, I see.
They don't overlap destructively. The receiver easily captures all these slow, parallel streams, reassembles them, and rebuilds the high-definition video perfectly, completely neutralizing the multipath reflections.
So OFDM is essentially a massive mathematical sorting algorithm happening in real time on the radio waves themselves. That explains how we get the beautiful video.
It does.
But I have a major pushback here, and it's something I think anyone listening who has ever tried to use public Wi-Fi will understand.
Oh, I know where this is going.
If these drones are blasting 2.4 and 5.8 gigahertz signals, the exact same frequencies used by literally billions of consumer Wi-Fi routers, Bluetooth headphones, smartwatches, and baby monitors across the planet, how on earth do they not just drown in a sea of civilian noise?
It's a great question.
Like, if I fly a drone over a crowded football stadium, shouldn't the thousands of iPhones in the stands just crush the drone's signal?
It's an incredibly important point, and it's where the pure engineering collides with federal regulation. The airspace is a shared resource. To prevent the scenario you're describing, regulatory bodies like the FCC in the United States or Ofcom in the UK enforce strict hardware limitations.
Okay.
The primary metric here is EIRP, which stands for Equivalent Isotropically Radiated Power.
Let's define EIRP, because it's not just the amount of electricity flowing from the battery into the radio, right?
No, it is a measurement of the actual RF power that is effectively radiated out of the antenna into the environment. The regulations strictly limit direct link drones operating on these civilian bands to a specific power output. For instance, the limit on 2.4 gigahertz is typically capped at 20 dBm.
20 decibel milliwatts, which, if we translate that from logarithmic math to standard power, is roughly 100 milliwatts, correct?
Correct. 1/10 of a single watt. To give you some context, 100 milliwatts is essentially the exact same transmission power limit as the Wi-Fi router sitting in your living room.
Wait, really?
Yes, really.
A drone flying miles away is using the same transmit power as my home router that struggles to reach my kitchen.
Yes, and that is highly intentional. By capping the transmission power so aggressively, the regulators ensure that drones don't become flying noise jammers.
That makes total sense.
If a commercial drone was allowed to pump out 50 watts of power on 2.4 gigahertz, it would deafen every consumer device for miles. It could potentially interfere with critical ground-based infrastructure or even localized aviation systems. They are forced to play nicely in the sandbox.
So how does it go so far, then?
The reason the drone can fly so far on such low power, while your router struggles, comes down to having highly specialized focused antennas and an unobstructed line of sight up in the sky.
Which makes perfect sense for a civilian context. Like, if you are inspecting a bridge or filming a wedding, everyone follows the FCC rules. You stay under 100 milliwatts, you use OFDM to handle the reflections, and the system works beautifully.
Exactly. It's an elegant system for a peaceful environment.
But as we dive into the military standards in these sources, specifically the sections dealing with contested airspace, the entire paradigm shifts.
The sandbox disappears entirely.
Right. In a hostile environment, the adversary does not care about the FCC. They are not capping their generators at 100 milliwatts.
Not even close.
They are rolling out dedicated electronic warfare units designed specifically to hunt down your radio frequencies and physically crush them with overpowering, deafening noise. The sources detail how traditional single-frequency radios are just flying targets.
They absolutely are.
You tune your drone to channel 4, the enemy spectrum analyzer sees the spike on channel 4, they blast it with static, and your drone falls out of the sky.
It is the brutal reality of the electronic battlefield. The inverse square law dictates that signal strength degrades exponentially over distance. If your drone is 20 miles away, its signal reaching the enemy jammer is a whisper.
Right.
But the enemy jammer on the ground has access to massive diesel generators and can pump tens of thousands of watts of localized noise into the sky. In a direct shouting match, the drone always loses.
So how do they survive? The specs detail a technology that sounds straight out of science fiction. FHSS, frequency hopping spread spectrum.
It is arguably one of the most important developments in secure communications. And what's fascinating here is the historical origin. The foundational concept wasn't developed in a modern Silicon Valley lab.
No?
No, it was famously co-patented during World War II by the Hollywood actress Hedy Lamarr and the avant-garde composer George Antheil.
Wait, Hedy Lamarr, the movie star.
Yes. They were trying to solve the problem of radio-controlled torpedoes getting jammed by the Axis powers. They realized that if a torpedo stayed on one frequency, the enemy could easily block it.
That makes sense.
So they conceptualized a system, initially using the physical paper rolls from a player piano, to constantly change the frequency of the transmission in sync with the receiver.
That is incredible. A player piano roll guiding a torpedo.
The military didn't adopt it at the time, unfortunately, but the mathematical concept was utterly sound. Fast forward to today, and the modern implementation in these UAVs is mind-bending. With
Mm.
FHSS, the drone and the ground station do not sit on a static channel.
So what do they do?
Before the flight begins, both the transmitter and the receiver are loaded with an identical, mathematically generated pseudo-random code.
Pseudo-random meaning it looks completely random to an outsider, but both radios know the exact sequence.
Precisely. This code dictates a frantic, unending sequence of frequency changes. They don't just move from channel 1 to channel 2. They hop from 400 megahertz instantly to 1.2 gigahertz, then down to 900 megahertz, then up to 2.4 gigahertz.
Right.
And they do this in absolute microscopic synchronization.
I was reading the speeds required by the Mylaris firmware mentioned in the sources, which utilizes advanced software-defined radio modules, or SDRs.
The SDRs are where the magic happens.
And the numbers are just staggering. We're not talking about hopping once a second. These SDRs completely divorce the actual radio hardware from the limitations of fixed silicon circuits. The software on an FPGA chip dynamically shapes the actual radio waves. They are executing over 2,000 hops per second.
Let's really pause and contextualize that speed. 2,000 hops a second. A microsecond is 1/1,000,000th of a second.
Right.
These radios are lingering on a specific frequency for a fraction of a single millisecond before utterly vanishing and reappearing in an entirely different part of the spectrum.
To put that in perspective, the blink of a human eye takes about 300 milliseconds. So in the time it takes you to blink, the drone and the controller have entirely changed their communication channel 600 times.
It is beyond human comprehension. And to an enemy trying to jam it, it presents an almost unsolvable physics problem. Well, if an adversary points a highly sophisticated spectrum analyzer at the sky, trying to isolate your drone's control link, they don't see a steady spike of data. A signal hopping 2,000 times a second doesn't register as a communication link.
What does it look like then?
It spreads its energy so thin across such a wide swath of spectrum that it just looks like a slight elevation in the ambient background thermal noise of the universe.
Wow. It hides in the static.
Yes. Narrowband jammers, which are designed to pinpoint a specific frequency and overpower it, are rendered entirely useless. By the time the jammer's computer detects the signal, calculates the frequency, and triggers the jamming burst, the drone hasn't just moved. It has already hopped 50 times to 50 different frequencies.
It's like trying to shoot a single dust mite that is teleporting across a football field 2,000 times a second, and you are trying to hit it with a sniper rifle. You can't track it, you can't predict it, and you certainly can't hit it.
You can't. Even advanced follower jammers that try to track the hops simply cannot compute and execute the physical hardware changes in the microsecond timeframes required. The SCRs are just too fast.
Which naturally leads to the brutal escalation of warfare. If you can't snipe the teleporting dust mite, you don't use a sniper rifle, you use a bomb.
Unfortunately, yes.
The sources detail what happens when the enemy realizes they can't track the hops. They roll out broadband barrage jammers. They don't try to find the specific channel. They just output millions of watts of raw garbage noise across the entire spectrum simultaneously. From 300 megahertz all the way up to 6 gigahertz, they just drown the entire valley in static.
And that is the ultimate nightmare scenario for a drone operator. If every conceivable frequency is saturated with high-power noise, hopping doesn't save you. You are just hopping from one incredibly loud room into another incredibly loud room.
So how does the drone survive the barrage? Because the military specs clearly show these systems continuing to operate even when completely bathed in broadband interference. This is where the engineering gets almost magical. We have to introduce CRPA.
Controlled Reception Pattern Antennas.
Right.
This is the definitive anti-jamming shield. To understand why CRPA is such a massive leap forward, we first have to look at the flaw in standard antennas. Let's look at the GPS receiver chip in your smartphone, or the standard stick antenna on a basic drone.
Okay.
These are generally omnidirectional antennas.
Meaning they listen in a giant sphere all around them.
Yes, they are passive, unbiased listeners. They receive electromagnetic energy equally from almost all directions. So if a friendly GPS satellite is whispering an incredibly faint signal from 12,000 miles out in space, and an enemy truck is screaming static from a hilltop 1 mile away, the standard antenna hears both.
And because of the inverse square law we talked about, the screaming truck completely overpowers the whispering satellite. The antenna just gets deafened.
It is basic physics. Loud noise drowns out quiet noise. But a CRPA system fundamentally breaks that paradigm. CRPA does not rely on a single antenna. It is an array.
Like a cluster of them.
It utilizes multiple independent antenna elements, usually 4, 8, or even up to 16 individual elements arranged in a very specific geometric pattern on the surface of the drone.
Yeah, I saw specific hardware mentioned in the documentation. Systems like the AGG microwave head GE 8008, which utilizes an 8-element array, or the Russian Kometa systems that use 4 to 8 channels. So you have this geometric cluster of antennas on the roof of the drone.
Correct.
But how does simply adding more antennas stop the noise? Doesn't that just give you 8 ears to get deafened instead of one?
It would if they were just passively listening. But the magic of CRPA happens in the advanced digital signal processing taking place behind the antennas. Because these individual elements are spaced slightly apart from each other, maybe just a few inches, the radio waves from the jamming truck do not hit all the elements at the exact same time.
Okay, let's visualize this. Say the truck is to the drone's left.
Right. The jamming wave will hit the leftmost antenna element a microscopic fraction of a nanosecond before it hits the rightmost antenna element.
Ah, a phase difference.
Exactly. The digital signal processor inside the CRPA is sampling the incoming signals billions of times a second. It analyzes these incredibly microscopic phase and amplitude differences between the elements. Using complex spatial algorithms, the processor instantly calculates the exact 3D vector of the incoming noise.
Wow.
It knows precisely where the jammer is located relative to the drone.
It pinpoints the screaming truck, but then what does it actually do with that information?
It executes a mathematical process called adaptive beamforming and null steering. The processor takes the signals from all the individual antenna elements and deliberately mathematically shifts their phases. It misaligns them.
So it's messing with its own reception.
It combines the signals in such a way that the wave peaks from one antenna perfectly cancel out the wave troughs from another antenna, but only for the signals arriving from that specific 3D vector.
So it artificially creates destructive interference.
Yes. It essentially creates a massive, perfectly shaped electronic blind spot called a null and dynamically points it right at the jammer. The jammer's effective power drops by 30, 40, sometimes 50 decibels. From the drone's perspective, the jammer is effectively erased from existence.
That is just, it's hard to wrap your head around. It's like standing in a crowded room where someone is blowing a literal air horn directly into your face. A normal person goes completely deaf,
Right.
but a person with CRPA ears instantly calculates the exact angle of the air horn, mathematically deletes all acoustic waves coming from that specific 12-degree angle, and simultaneously cups their hands around their ears to focus entirely on a friend whispering from across the room.
That is a phenomenal analogy. The CRPA creates the blind spot for the jammer and simultaneously uses that same beamforming math to create a high-gain, highly focused beam pointing straight up to the friendly satellites. It manipulates its own perception of reality to survive.
And as I look at these white papers, the implications of this are massive. This isn't just a neat trick, this is the hard dividing line in modern aerospace. This is the difference between a high-end consumer toy that helplessly falls out of the sky the second it flies near a high-power TV broadcast tower, and a tactical machine that can thread the needle through military-grade electronic warfare.
It is a mandatory survival requirement. You cannot operate a modern tactical UAV in a contested environment without CRPA. The airspace is simply too hostile.
It's a complete arms race happening invisibly all around us. We have SDRs hopping 2,000 times a second. We have antennas bending space and time to create blind spots.
What's wild?
But before we transition away from the physical radio waves, I noticed a tiny detail in the specs that felt almost out of place. Amidst all this quantum-level complexity, the sources still mandate the use of the FRSky link bus for certain operations. FRSky is a very old, very basic, near-field RC protocol.
Yes, it is.
Why is a drone that can mathematically delete radio waves still using a protocol you'd find in a hobbyist's RC airplane?
Because physics always demands a toll, and in this case, the toll is latency. When you are processing frequency hops and executing complex cryptographic algorithms and mathematically shaping antenna beams, all of that computation takes time. It might only be 50 or 100 milliseconds, but it is a delay.
And if a human operator is standing on the side of a ship, manually flying a massive drone onto a pitching deck in high winds?
A 100-millisecond delay means the drone crashes into the deck.
Exactly.
When a human is physically pushing a joystick to control aerodynamic surfaces in the near field, you need absolute deterministic immediacy.
So they use FRSky.
Right. FRSky doesn't have massive bandwidth. It has virtually no security, but it is an ultra-low latency, bare metal physical connection. When you push the stick left, the ailerons move left instantaneously. It ensures the human reflexes aren't buffered by digital bureaucracy.
Okay, so that perfectly maps out our physical layer. We have the invisible wire connecting the pilot to the machine, secured by hopping through the spectrum and using smart antennas to ignore the noise.
That's the foundation.
But having a clear radio channel is just the beginning. Just because a telephone line is connected doesn't mean the people on either end speak the same language.
Yeah.
This leads us to the internal architecture of the drone. Once the physical signal arrives, how is the actual data formatted? What are they saying to each other?
This is where we transition from the realm of the hardware engineers, the antenna designers and RF physicists, into the realm of the software architects. You need standardized data link protocols to translate raw radio waves into actionable computer commands.
Makes sense.
And for the critical air-to-ground link, the conversation between the drone and the ground control station, or GCS, the undisputed heavyweight standard across the industry, is MAVLink.
MAVLink, Micro Air Vehicle Link. This protocol is plastered all over the documentation, but the white papers spend an enormous amount of time specifically detailing the transition from MAVLink version 1 to MAVLink version 2. Clearly, something forced the industry to completely overhaul the system.
Oh, absolutely.
I was looking at the history here, and it seems MAVLink v1 was a massive vulnerability. Like, it was entirely plain text.
It was. Version 1 was designed in an era where drones were mostly experimental or confined to academia. The designers prioritized making the protocol incredibly lightweight and efficient. Every single byte mattered. But because of that, it had zero authentication and zero encryption.
Which means, in a practical sense, it was the digital equivalent of shouting commands in a crowded room. If I was flying a drone using MAVLink v1 and you were sitting nearby with a laptop and a cheap radio antenna, you didn't just see my drone's data, you could inject your own.
You could seamlessly hijack the machine. You could broadcast a packet formatted as a standard mission item command, overwrite the drone's internal GPS waypoints, and tell the autopilot to turn around and land in your backyard.
That's terrifying.
Or worse, you could use a parameter set command to alter the drone's PID tuning, the parameters that keep it stable in the air, and force it to flip over and crash. The drone's computer had absolutely no way to distinguish a legitimate command from the pilot from a malicious command from a hacker.
That is an absolute cybersecurity nightmare. Imagine a multi-million-dollar piece of flying infrastructure being hijacked by a teenager with a $50 software-defined radio.
It was a very real threat.
So they rush out MAVLink version 2 to stop the bleeding. The core of this upgrade, according to the specs, is something called SHA-256 message signing. Let's really break this down. How does a digital signature actually stop someone from hijacking the drone?
It relies on cryptographic math. Before the drone ever leaves the ground, the operator connects it to the ground station, usually via a secure physical USB cable. They generate a 32-byte secret key, essentially a highly complex password.
Okay.
This key is stored securely in the memory of the drone and in the memory of the ground control station. It is a shared secret.
So both sides know the password.
Exactly. Now, let's say the drone is in the air and the pilot wants to send a command to return to launch. The ground station software takes that command and it adds a highly precise timestamp to it. Then it takes the command, the timestamp, and that 32-byte secret key and runs all of it through a one-way hashing algorithm called SHA-256.
A one-way hash, meaning you can scramble the data into a fixed output, but you can never mathematically reverse the output back into the original data.
Correct. The algorithm churns all that data and generates a unique 48-bit digital signature. The ground station appends this signature to the end of the command packet and transmits it over the radio waves.
So the hacker intercepts this packet in the air. They see the command, they see the signature, but they don't have the 32-byte secret key.
Right. Meanwhile, the drone receives the packet. It strips off the signature. It takes the raw command, looks at the timestamp, and runs it through its own internal SHA-256 algorithm using its own copy of the secret key.
And it generates its own hash.
Exactly. It generates a hash.
Yeah.
It then compares its mathematical result against the signature that was attached to the packet.
And if they match perfectly, byte for byte.
The drone knows two things with absolute cryptographic certainty. First, it knows that whoever sent the message must possess the secret key, therefore verifying it is the legitimate ground station.
Okay, that's one.
Second, it knows that not a single 0 or 1 in the command was altered in transit. Because of the avalanche effect in SHA-256, changing even a single bit of the command would result in a completely radically different hash signature.
That is elegant. But wait, what if the hacker is clever? What if they just record the legitimate, perfectly signed return to launch command out of the air and then play it back to the drone an hour later when they want to disrupt the mission? The signature is valid, right?
This is a classic replay attack, and it's exactly why the timestamp is inextricably bound into the hash. When the drone receives the command, it checks the timestamp. If the command is stamped with a time that is more than a few milliseconds old, the drone's software simply rejects it.
It just ignores it.
It ignores the command entirely. The cryptographic window of opportunity closes instantly. MAVLink v2 decisively secures the authenticity and the integrity of the command link. You cannot hijack the drone.
Which is a massive victory for security. But here is where the source material drops a bombshell, and I want to spend some time on this because it feels like a massive oversight.
Yes, the elephant in the room.
MAVLink v2 uses these incredibly complex cryptographic signatures to prove who sent the message. It is like taking a highly sensitive letter, stamping it with an intricate, impossible-to-forge wax seal, and putting a strict postmark on it. The receiver knows exactly who sent it, and they know nobody tampered with the letter.
That is a perfect analogy for authentication.
Right, but they put that letter inside a completely transparent envelope. The sources are explicitly clear. MAVLink v2 provides authentication, but it does not provide payload encryption.
You have zeroed in on a critical vulnerability that even some systems engineers failed to grasp initially. Authentication and confidentiality are two entirely different pillars of cybersecurity. MAVLink v2 guarantees that nobody can maliciously control your drone. But the actual data, the payload, remains entirely in plain text.
So what does that actually look like in the real world? Let's paint a scenario.
Imagine you are operating a commercial drone, conducting a highly sensitive inspection of a new, unannounced prototype vehicle on a test track. You're using MAVLink v2. Nobody can crash your drone.
Okay.
But a corporate spy sitting in a car a mile away with a directional antenna and a laptop can read every single byte of telemetry your drone sends back to your controller.
In plain text.
In plain text. They can see the drone's exact 3D GPS coordinates updating 10 times a second. They can read the pitch, roll, and yaw, meaning they know exactly where the camera gimbal is pointing. They can read your battery voltage down to the millivolt.
Which means they know exactly how much flight time you have left before you are forced to land. They can literally calculate your operational endurance.
Precisely. In a tactical military scenario, leaking unencrypted telemetry is a catastrophic failure. If the adversary knows exactly where the drone is looking, they can deduce your tactical intent. They know what you are interested in.
So how do the engineers solve this? If MAVLink v2 leaves the envelope transparent, how do you hide the letter?
The white papers explicitly state that for sensitive operations, you cannot rely on the protocol layer alone. You have to move the security down to the transport or hardware layer. Operators must wrap the entire MAVLink data stream inside a virtual private network, or VPN, or utilize radios that possess hardware-level AES-256 encryption on the actual transmission layer.
So you lock it up?
You have to take that transparent envelope and lock it inside a heavy steel lockbox before you transmit it through the air. MAVLink guarantees the commands. The hardware encryption hides the data.
Okay, that covers the air-to-ground link, the external conversation. But a modern drone isn't just a single computer chip connected to some propellers. It is an incredibly dense, sophisticated network of internal organs.
It really is.
You have the central flight controller, which is the brain. You have the electronic speed controllers, the ESCs, which are the muscles driving the motors. You have the battery management system, the GPS modules, the optical flow sensors. How do all these disparate organs talk to each other inside the chassis of the drone?
Historically, internal drone communication was a mess. It relied on simple, point-to-point analog or digital connections. You used pulse width modulation to tell the motors how fast to spin. You used I2C for the compass. You used serial UARTs for the GPS. As drones became more complex, adding dozens of sensors, this turned into an absolute nightmare of wiring harnesses.
More wires mean more weight and more points of physical failure.
Exactly. And it also introduced critical latency bottlenecks. So the industry underwent a massive architectural shift. They adapted a technology originally designed by Bosch for the automotive industry, the CAN bus, Controller Area Network.
CAN bus. This is the exact same underlying technology that connects the anti-lock brake sensors to the engine computer in my Honda Civic, right?
The exact same physical principle. It uses a single twisted pair of wires, just two wires, that runs throughout the entire vehicle. Every single component simply taps into that one central spine.
Okay, that simplifies things.
It does. But modern drones utilize a much faster variant called CAN-FD, flexible data rate, which provides bandwidths up to 8 megabits per second. However, the real revolution outlined in these sources isn't the physical wire. It is the software protocol running on top of it. Specifically, protocols called Cyphal, which was formerly known as UAV CAN version 1, and Drone CAN.
I was reading about Cyphal, and it fundamentally changes the philosophy of how the internal computers relate to one another. The documentation contrasts the old way, a master-slave architecture, with Cyphal's approach, which is called a stateless, publish-subscribe architecture. Let's break this down. What was so dangerous about the master-slave setup?
In a master-slave architecture, the central flight controller is the absolute dictator. It is the master. Every other component, the GPS, the battery, the motors, is a slave. The master must constantly individually poll every single sensor to get information.
It has to run down a checklist.
Yes. It asks GPS, what are your coordinates? The GPS answers. Battery, what is your voltage? The battery answers. The entire network relies entirely on the master's processing loop.
So it's bottleneck.
Exactly. If the flight controller experiences a microsecond glitch, or if the polling schedule gets bogged down by a heavy calculation, the flow of data stops. The slaves don't speak unless spoken to. If the master computer crashes and reboots, the entire drone falls out of the sky because the communication spine collapses.
It's an inherently fragile hierarchy, a single point of failure. So how does publish-subscribe, this Cyphal architecture, fix the fragility?
In a publish-subscribe network, the hierarchy is abolished. There is no master. Every single component plugged into the CAN bus is considered an equal node on the network. The GPS module doesn't wait to be asked for its location.
What does it do?
It just constantly, autonomously publishes its coordinate data onto the central wire. It broadcasts it to the entire network, and it frankly doesn't care who is listening.
It just shouts its truth into the void.
Exactly. Meanwhile, any component that actually needs that location data simply subscribes to that specific message ID. The flight controller subscribes to the GPS data to navigate. But the camera gimbal might also subscribe to the exact same GPS data simultaneously, using it to calculate the angle needed to keep a specific target in frame.
That is a brilliant analogy. It's the difference between a rigid corporate hierarchy and a modern social media newsfeed. In the old master-slave setup, the CEO, the flight controller, has to personally walk around the office and ask every single employee for a status update. It's incredibly inefficient.
Right.
In publish-subscribe, every employee just posts their status update to the company's internal Twitter feed.
Yeah.
Whoever needs the information just scrolls the feed and reads it.
That captures the efficiency perfectly. But the real benefit is the staggering resilience this stateless design provides. The sources highlight an extreme worst-case scenario: an electromagnetic pulse, or a massive burst of directed RF interference.
An EMP, something that physically overwhelms the circuitry.
Right. An event severe enough that it forces the microcontrollers on the drone to physically brown out and reboot. Imagine a drone gets hit by a localized burst of interference, and the electronic speed controller for the front right motor crashes.
In a master-slave system, the central flight controller would poll the ESC, get no response, throw a critical hardware failure error, and potentially trigger a total system shutdown.
But in Cyphal, because the system is entirely stateless, there is no master connection to break. The ESC's microcontroller loses power, reboots, performs its split-second internal self-check, and simply starts publishing its RPM data and subscribing to thrust commands again. It seamlessly rejoins the flow of traffic on the network.
It just picks up right where it left off.
The specs state that this architecture allows a node to suffer a total power cycle and restore full thrust control in less than 10 milliseconds. To the human eye, the drone might violently shudder for a fraction of a second, but it recovers and keeps flying. It is a decentralized, self-healing nervous system. It is incredibly robust.
That level of resilience is mind-blowing. And there was another detail buried in the Cyphal specifications that I absolutely loved because it addresses a fundamentally human flaw rather than a hardware flaw. It has to do with how the protocol handles units of measurement.
Ah, yes. The strict enforcement of the International System of Units, the SI units, within Cyphal's Data Structure Description Language, or DSDL.
When I first read that, I thought, why is a software protocol dictating the metric system? But when you look at the history of aerospace engineering, unit confusion is one of the most deadly and expensive sources of human error in existence.
It absolutely is. You cannot understate how dangerous a simple unit mismatch can be.
The most famous example, of course, is the 1999 Mars Climate Orbiter. NASA spent $125 million sending a probe to Mars. The spacecraft arrived, fired its engines to enter orbit, and promptly disintegrated in the Martian atmosphere.
To a total loss.
Right. Why? Because the engineering team at Lockheed Martin was calculating the engine thrust using English imperial units, pound-seconds. But the navigation team at NASA's Jet Propulsion Lab had programmed the onboard computer expecting metric units, newton-seconds. The computer thought the thrusters were firing with a fraction of the power they actually were. The probe went completely off course and burned up, all because a piece of software didn't explicitly define what the numbers meant.
And that same risk exists exponentially in modern drones because operators are constantly mixing and matching hardware from different global manufacturers.
Oh, I see where this is going.
Imagine you build a custom commercial drone. You install a specialized third-party payload sensor that broadcasts temperature data over the CAN bus in Fahrenheit. But the drone's central battery management system was coded in Europe and interprets all temperature integers as Celsius.
The sensor could be screaming that the battery is at 150 degrees Fahrenheit, which is dangerously hot, practically melting.
Yeah.
But the battery management system reads the number 150, assumes it means 150 Celsius, and the logic says, oh, 150 is the red line limit, but we aren't quite there yet, keep flying. The drone catches fire and falls out of the sky.
Precisely. Cyphal mathematically eliminates this entire category of catastrophic bugs at the protocol level. If you're an engineer writing software for a Cyphal-compliant node, you do not get to choose your units. The protocol rigidly enforces SI standards. Rotational speed, like node RPM, must be expressed in radians per second. Atmospheric pressure must be expressed in pascals. Temperature must be transmitted in Kelvin.
You literally cannot write a compliant packet of data that contains Fahrenheit or PSI. The protocol won't compile it.
It is forced standardization. It means you can take a flight controller manufactured in Switzerland, a motor ESC coded in Taiwan, and a specialized LiDAR sensor built in the United States, plug all three of them into the same twisted pair of wires, and know with absolute 100% mathematical certainty that they all agree on the fundamental nature of the universe. It is a brilliant example of using software architecture to prevent human error.
Okay, so we have the air ground link secured with authenticated MAVLink packets. We have the internal organs humming along resiliently, self-healing from EMPs on the Cyphal CAN FD bus. But as we dig into the final section of the protocol specifications, the sources pivot away from basic flight mechanics and focus heavily on the cutting edge of modern robotics artificial intelligence.
This is where the physical limitations of the CAN bus become apparent. The AI edge.
Right. The white papers describe drones that are no longer just remotely piloted vehicles. They carry onboard companion computers, massive processing units like the NVIDIA Jetson Orin series. These are essentially flying supercomputers processing complex machine vision algorithms in real time. But the specs are very clear. Standard protocols like Cyphal, even running at 8 megabits per second on EMFD, are utterly insufficient for AI. Why is the internal network suddenly too slow?
To understand this bottleneck, you have to look at the sheer volume of data an AI brain requires to function. Cyphal is incredibly reliable for transmitting a temperature reading or a GPS coordinate. That is a tiny packet of data, but an AI brain needs to actually see the world. Drones achieve this using LiDAR light detection and ranging in stereo-optical cameras.
Unpack LiDAR for us briefly because it generates a staggering amount of information.
A LiDAR spinning on the front of a drone is firing millions of microscopic laser pulses every single second. It measures exactly how long it takes for each pulse of light to bounce off an object, a tree branch, a building, a power line, and return to the sensor.
Wow.
By calculating the time of flight for millions of lasers, it builds a highly precise, continuously updating 3D topographical map of the world called a point cloud.
It's essentially creating a real-time virtual reality model of the environment.
Yes, and that point cloud is a massive fire hose of raw data. If your drone is flying at 100 miles an hour autonomously through a dense forest, the AI brain has to ingest that massive point cloud, calculate that a specific cluster of pixels is a tree branch in its flight path, calculate an evasive maneuver, and send that maneuver command to the flight controller.
And the margin for error is non-existent. If that entire computational loop takes an extra 50 milliseconds, the drone has already traveled another 7 feet and smashed into the tree.
Exactly. The latency must be virtually zero. So the engineers introduced a completely different architectural bridge for the AI, XRCE DDS, specifically the Micro XRCE DDS protocol.
Okay, that is a dense acronym. Let's break it down. What does this bridge actually connect?
It acts as a hyper-fast direct neural pathway. On one side, you have the drone's primary flight controller, running a highly deterministic real-time operating system. On the other side, you have the massive NVIDIA companion computer running ROS2, the robot operating system.
Okay.
Micro XRCE DDS bridges the two.
Oh, it doesn't use the CAN bus wires.
No, it bypasses the CAN bus entirely. It utilizes high-speed hardware connections, specifically UART or SPI buses, physically wired directly between the two computer boards.
So it's a direct link.
Yes. Micro XRCE DDS strips away all the translation layers and overhead. It allows the massive AI brain to reach directly into the flight controller's internal memory and read the raw IMU data.
I want to stop on IMU because it's a critical concept. Inertial measurement unit. I've always thought of the IMU as the drone's inner ear.
That is exactly what it is. The IMU contains microscopic gyroscopes and accelerometers that measure the physical forces acting on the drone, gravity, acceleration, rotational speed, thousands of times a second. It is the absolute core of how the drone knows its orientation in physical space.
So by using micro XRCE DDS over a high-speed SPI connection, the AI brain isn't waiting for the flight controller to package up an update and publish it to a network. The AI brain is directly reading the drone's inner ear in real time, achieving sub-10 millisecond latency.
Precisely. It is the technological equivalent of a biological reflex arc. When you accidentally touch a hot stove, your brain doesn't have time to consciously process the pain, formulate a plan, and send a signal down your arm.
Right, you just pull away instantly.
The sensory neurons send a signal to your spinal cord, which instantly fires a motor command back to your muscles. Your hand jerks back before you even realize you are burned.
The processing happens at the edge of the nervous system.
Yes. Micro XRCE DDS gives the robot spinal reflexes. It allows the drone to visually spot a high-voltage power line using its LiDAR, process the threat in the neural network, and bypass the conscious processing loop to instantly fire the specific ESCs required to roll the drone away from the wire, all in a fraction of a single second. It is the architecture of superhuman reaction times.
It is truly staggering to synthesize all of this. Let's just pause and look at what we've mapped out so far. We have a machine that can physically dodge enemy radio jammers by hopping across the spectrum 2,000 times a second, while using smart antennas to mathematically bend the shape of radio waves to create blind spots. We have a machine that cryptographically signs every single command it receives to prevent hackers from hijacking it. It has an internal nervous system that can suffer a catastrophic EMP blast, reboot, and heal itself in 10 milliseconds. And it possesses an AI brain wired with high-speed digital reflex arcs that can process 3D laser maps to dodge obstacles at 100 miles an hour.
It is a profound marvel of modern systems engineering.
But this leads to our final and, frankly, most pressing issue. An issue that moves us out of the realm of pure engineering and squarely into the realm of public safety.
This is where things get complicated.
With all of these incredibly smart, invisible, virtually unjammable robots flying around our cities, how do we keep them from crashing into each other? Or worse, how do we keep a massive commercial delivery drone out of the jet engine of a Boeing 737 full of passengers? This brings us to the third core concept in the sources: remote ID. The digital license plates of the sky.
This is the exact point where rapid technological innovation collides head-on with federal public policy and airspace management. For a very long time, the drone industry outpaced the regulators. The low-altitude sky was essentially the Wild West. But the law has caught up, and it is reshaping the entire architecture of the industry.
The sources repeatedly cite FAA Part 89 in the United States and similar comprehensive EASA regulations in Europe. What is the fundamental regulatory reality that operators are facing right now?
Under rules like FAA Part 89, the mandate is absolute. Virtually any drone weighing over 250 grams, which is roughly half a pound, basically anything larger than a micro toy that operates in controlled airspace, must be equipped with a functional remote identification system.
I was looking at the specifications for remote ID, and I have to push back a bit on the common analogy. People always call it a digital license plate, but a physical license plate on a car is entirely passive. It only works if a police officer is physically standing there with a radar gun to read it. If I speed through the desert with no cops around, the license plate does nothing. Remote ID seems far more active than that.
It is vastly more active. The license plate analogy is useful for explaining the basic concept of accountability, but it fails to capture the systemic utility.
Okay, explain that.
Well, if you connect this to the bigger picture, remote ID is the absolute foundational bedrock of what the aerospace industry calls deconfliction. We are rapidly moving toward a near future filled with urban air mobility, flying taxis, automated medical delivery drones, police surveillance UAVs, and local news helicopters, all trying to share the exact same low-altitude airspace over densely populated cities.
And you simply cannot manage that volume of traffic using traditional methods. A human air traffic controller sitting in a tower looking at a sweeping radar screen cannot manually deconflict 10,000 autonomous delivery drones swarming over Manhattan.
They cannot. The airspace management must be entirely algorithmic and automated. But a computer algorithm cannot manage what it cannot mathematically see. Remote ID is the mechanism that makes every single drone digitally visible to the overarching system.
And the sources break this visibility down into two distinct technological methods, depending on the scale of the operation. Let's unpack the first one, which is highly localized. Direct Broadcast Remote ID.
Yes, this is governed by the ASTM F3411 technical standards. Direct broadcast is exactly what it sounds like. The drone is equipped with a dedicated transmitter, usually utilizing ubiquitous protocols like Bluetooth 4.0, Bluetooth 5.0, or standard Wi-Fi broadband that simply shouts its telemetry into the void continuously from the moment the rotors spin up to the moment it lands.
What exactly is inside that shouted data packet? Because I assume it's more than just, hey, I'm a drone.
It is a highly specific, mandated payload of data. It contains a unique serial number or a session-specific digital ID. It contains the drone's highly precise 3D latitude and longitude, its barometric altitude above the ground, its real-time compass heading, and its velocity.
So if I am a concerned citizen standing in a public park and I hear a buzzing overhead, I can theoretically pull out my smartphone, open a specialized receiver app, and see exactly where that drone is, who it belongs to, and how fast it is moving.
Yes, that is the primary intent of direct broadcast, transparency. But crucially, the federal regulation requires the drone to broadcast one more deeply controversial piece of data: the precise physical GPS coordinates of the ground control station.
Wow.
Yes, the exact location of the human pilot holding the remote control.
Oh, wow. Okay, I can see how that changes the dynamic completely. That has massive privacy and security implications.
It does, and it has been the subject of intense debate. From a privacy advocate's perspective, or even from a commercial operator's perspective, say, a photographer who doesn't want to be harassed while working broadcasting your exact physical location to anyone within a mile radius who has a smartphone is deeply concerning.
But from the perspective of law enforcement and airspace security, it makes total sense. If a rogue operator is flying a drone illegally near the glide path of a major international airport or hovering dangerously low over a crowded football stadium, the authorities don't have to scramble a helicopter or try to shoot the drone out of the sky.
Exactly. They simply use a standard receiver to triangulate the direct broadcast remote ID signal, pull the GPS coordinates of the control station, walk straight over to the person holding the controller, and arrest them. It provides immediate, localized accountability.
Okay, so direct broadcast solves the problem of local accountability. If you are flying in a park, the people around you know who you are. But it completely fails to solve the macro air traffic control problem we discussed earlier. Bluetooth and Wi-Fi signals degrade rapidly. They only reach a few hundred meters. What happens when a massive logistics company like Amazon or UPS wants to launch a fleet of 5,000 delivery drones across an entire metropolitan area flying beyond visual line of sight?
Local Bluetooth shouting is useless at that scale. A delivery drone 10 miles away physically cannot hear the Bluetooth signal of another drone it is on a collision course with, which is why the engineering specs outline the necessary transition to networked remote ID and the integration of UTM Unmanned Aircraft System traffic management.
Let's explore networked remote ID. How does the industry scale this visibility up to a global level?
Instead of relying on short-range localized shouting, advanced commercial and enterprise drones are equipped with onboard cellular modems. They utilize 4G LTE, or the high-speed, low-latency 5G cellular network infrastructure that already blankets our cities.
Okay, using the cell towers.
Exactly. They use these cellular links to continuously stream their telemetry, their ID, exact location, speed, and projected trajectory up into a cloud-based server.
So the drone is essentially logging into the internet and reporting its status to a central database.
Yes. These databases are managed by authorized entities known as UAS service suppliers, or USS platforms. Multiple USS platforms securely share their data with one another to form the overarching UTM system. You can think of the UTM as a massive, omniscient, algorithmic air traffic controller designed specifically for the low-altitude drone economy.
So how does the UTM algorithm actually physically stop two drones from crashing into each other? Because if they are both flying at 60 miles an hour, by the time the algorithm detects they are too close and sends a message down over 5G to turn left, it might be too late. The latency of the cellular network could be fatal.
And that is exactly why the UTM does not primarily rely on real-time active dodging. The specs detail a concept called strategic deconfliction. The crash is prevented before the drones even leave the ground.
Walk me through a scenario. How does strategic deconfliction work?
Let's say a hospital needs to urgently transfer a payload of medical supplies to a clinic across the city. The operator's ground station software connects to the UTM cloud and submits a highly detailed planned flight path. But it's not just a line on a map. It is a 4D flight plan.
4D meaning the three spatial dimensions, latitude, longitude, altitude, plus the dimension of time.
Exactly. The flight plan dictates the precise 3D route and the exact millisecond the drone plans to occupy every single cubic meter of airspace along that route.
Okay, so the hospital submits the 4D tube of airspace they want to claim.
Right. The central UTM algorithm receives that request. In a fraction of a second, it mathematically compares your proposed 4D tube against the planned approved trajectories of every single other drone registered in the system across the entire city. It also cross-references dynamic data, like temporary flight restrictions caused by a fire or a medical helicopter landing nearby.
It analyzes the entire interconnected web of the city's airspace.
Yes. And if the algorithm detects that your planned flight path intersects with the flight path of a pizza delivery drone 3 miles away at exactly 2.14 p.m. and 30 seconds, it instantly rejects your flight plan.
It just says no.
It denies clearance. It mathematically forces the hospital drone operator to either alter their route, perhaps flying a block to the north, or delay their takeoff by a few minutes before they're ever allowed to start their rotors.
That is wild. It's essentially playing an impossibly complex game of 4D chess with thousands of flying robots simultaneously, predicting the future to ensure that two pieces never occupy the same square at the same time.
It is the only mathematical way to scale the industry. Because once they are in the air, flying at high speeds through urban canyons, relying solely on onboard LiDAR to dodge unexpected traffic, is incredibly dangerous. Strategic deconfliction guarantees that the intersection never occurs in the first place.
It's a proactive solution.
Exactly. This global 5G networked integration is the foundational architecture required to safely enable millions of autonomous commercial drone flights a day.
Okay, we have covered a truly staggering amount of technical ground today. Let's synthesize this journey. We started by looking at the invisible physical battlefield of radio waves. We saw how operators utilize the diffraction of 1.4 gigahertz S-bands for long-range, terrain-hugging telemetry.
A great foundation.
We explored how tactical systems survive active electronic warfare by employing software-defined radios to execute over 2,000 frequency hops every single second, effectively hiding in the static. And we unpacked the science fiction reality of CRPA smart antennas, calculating phase differences to literally warp the shape of radio reception and create digital blind spots aimed precisely at enemy jammers.
From that physical foundation, we moved into the software protocols, the languages they speak. We analyzed how MAVLink version 2 utilizes complex SHA-256 cryptographic signatures to definitively prove authenticity and prevent hackers from executing replay attacks to hijack the drone.
Right, while also exposing the critical flaw that the payload data remains entirely unencrypted, requiring hardware-level VPNs to hide sensitive telemetry.
Exactly.
We then explored the internal nervous system, breaking down the brilliance of the Cyphal CAN FD bus. We saw how moving from a fragile master-slave hierarchy to a decentralized publish-subscribe model allows the internal organs to seamlessly recover from catastrophic EMP blasts and restore thrust control in under 10 milliseconds.
A huge leap forward.
We even dove into the history of the Mars Climate Orbiter to understand why Cyphal rigidly enforces SI units to prevent deadly software bugs. And we saw how Edge AI is integrated using the micro XRCE DDS protocol, bypassing the network to give the robotic brain sub-10 millisecond spinal reflexes for high-speed obstacle avoidance.
Finally, we navigated the regulatory framework of remote ID, seeing how the industry is evolving from drones shouting their pilots' physical coordinates over local Bluetooth for accountability toward a globally networked 5G UTM system that acts as an omniscient algorithmic air traffic controller.
Right, utilizing 4D strategic deconfliction to prevent collisions before the drones even leave the ground. You are now armed with a truly deep, comprehensive understanding of the incredibly complex, invisible data architecture that is keeping our modern skies functioning.
However, As is so often the case when you study advanced systems engineering, there is a fascinating paradox hidden deep within these strategic white papers, a counter trend that completely upends everything we have discussed.
Oh, we spent an hour building this invisible world. What breaks it? Lay
Hang
it
on.
on me.
Well, we have spent this entire deep dive marveling at the most advanced wireless technology humanity has ever created. Software-defined radios, dynamic frequency hopping, 5G network integration, algorithmic beamforming. But the tactical documents reveal that in the most extreme, highly contested electronic warfare environments, where the adversary's jamming power is so overwhelming, so absolute, that even hopping 2,000 times a second and utilizing 16-element CRPA antennas isn't enough to punch through the noise.
What do they do?
The ultimate solution engineered for drone communication is incredibly, almost comically old school.
How old school are we talking? What do you do when the entire electromagnetic spectrum is weaponized against you?
You abandon the wireless spectrum entirely. The latest highly specialized tactical drone designs feature a physical modification. Mounted deep within the drone's chassis is a precision-engineered spool.
A spool?
Yes. As the drone takes off and flies across the battlefield, it literally unspools 10 to 20 kilometers of ultra-thin, highly durable glass fiber optic cable directly behind it.
Wait, a physical wire. They are flying a massive AI-powered drone by dragging a wire behind it.
A literal, physical glass thread. It physically connects the flying drone all the way back to the operator's ground station. By translating the high-definition video feeds and the flight control commands into pulses of light and shooting them down a physical glass fiber, the drone creates what the military terms a zero-signature communication link.
And because it's just photons bouncing around inside a glass tube, it doesn't emit any radio waves into the air.
Exactly. It emits absolutely zero RF radiation. To an enemy spectrum analyzer, the drone does not exist. It is completely electronically invisible.
That is wild.
And conversely, because the data is trapped inside the glass, completely physically isolated from the surrounding electromagnetic spectrum, it is 100% immune to all forms of jamming, spoofing, or interference. You could detonate a massive electromagnetic pulse mere feet away from the fiber line, bathing the battlefield in debilitating noise, and the high-definition video feed flowing through the glass wouldn't even drop a single frame.
That is just brilliant. A multi-million-dollar flying robot packed with artificial intelligence, LiDAR point clouds, and the most advanced cryptographic microprocessors humanity has ever created, ultimately saved in the absolute worst-case scenario by a really long string.
It perfectly captures the irony of complex engineering. Sometimes when the invisible wireless war becomes utterly unwinnable, the ultimate, most sophisticated solution is simply to plug the machine back into the wall.
I absolutely love that. The elegance of a physical wire defeating a billion-dollar electronic warfare system. Well, that is all the time we have for today. Thank you so much for joining us on this incredibly expansive deep dive into the hidden nervous system of modern unmanned aerial vehicles.
It's been a great discussion.
It really has. The next time you look up and see one of these machines hovering silently in the park or tracking a pipeline on the horizon, we hope you remember just how loud, chaotic, mathematically precise, and impossibly complex the invisible world surrounding it truly is. Keep questioning the invisible networks all around you.